Hello everybody. In this video lesson, we are going to look at how our kidneys make urine. Now, this is the second part of the excretory system. The first video talked about the different organs. We talked about, the capsules, the layers around the kidneys. We talked about the three parts of the kidney, the cortex, the medulla, the pelvis. We talked about the bladder and the ureter and the urethras and all these different tubes. And so that was more of the structure. This video is going to look at the function of the kidneys and how our kidneys actually make urine. Now, first of all, we got to talk about the blood that comes to the kidneys. Now, inside of your kidneys, we have the outermost layer is what we call the renal cortex, and not much happens there. The renal medulla has this folded pattern, if you remember, called renal pyramids, and that's where we find these guys called nephrons. Nephrons are the functional units of our kidneys. Think of our kidneys as having hundreds of vacuum tubes in them. And just like a vacuum goes around and sucks things up from your house, from the floor, think of these nephrons as sucking things out of your blood. So all of these nephrons, you have hundreds of nephrons per renal pyramid. And each of these would be like a little vacuum tube that's going to help take waste products out of our bloodstream. But we have a little problem, okay, as you're going to see here in a second. But in the case of the nephron, since the job of the nephron is to filter the blood, we obviously have to have a blood supply that comes to it. So we have the renal artery. Remember, the renal artery is the main artery that comes to the kidneys. Anytime you see renal, that means kidneys. And the renal artery is carrying what I call dirty blood to the kidneys. Well, the renal artery will then begin to split. And remember, every time it splits, it gets a little bit smaller and a little bit smaller and a little bit smaller. Well, eventually, the renal artery will split into these things called arterioles. Remember, an arteriole is a small artery. Remember, by definition, an artery has 3 layers. In the case of an arteriole, it's only going to have 2 layers. So we had to change the name a little bit, but it's still carrying blood away from the heart. But in the case of our kidneys, our renal artery will split and split and split to form all of these things that we call afferent arterioles. And so, in the case of this diagram, this right here would be just one afferent arteriole. Okay, so we've got the renal artery, and you can see how in this picture that this blood vessel is smaller. Well, the afferent arteriole is going to be responsible for carrying blood to the nephrons. Now, they will also continue to split until we make a ball of capillaries. If you remember from our circulatory system lessons, we go from an artery, which is 3 layers thick, to an arteriole, which is only 2 layers thick, to a capillary, which is only 1 layer thick. And capillary is where all diffusion and osmosis takes place. So in the case of our blood supply to the nephron, we have this thing called an afferent arteriole. The afferent arteriole will then continue to split until it forms a capillary bed. And that's this thing right here. And that capillary bed is called the glomerulus. Now, each nephron has its own capillary bed. Okay? So think of the capillary bed as a rug, and then the nephron is a vacuum. And you know the head of the vacuum, that's the part that you run across the rug to suck things up? Well, we have the head or the start of the nephron. And that's this portion right here. You can see how it's wrapped around our ball of capillaries. And that start to our nephron you're going to see is called the glomerulus capsule, because it's a capsule around this ball of capillaries. It's also called the Bowman's capsule. But anyway, when blood enters the kidney, it's going to enter as the renal artery. The renal artery will begin to split into these things here that we call our afferent arterioles. And then our afferent arterioles will split and form these capillary beds that we call the glomerulus. Now, the glomerulus is going to take the blood to the nephron. So each nephron has its own capillary. So, and think of the nephron as this huge vacuum. This is the tube inside the kidney that actually does the filtering. You have hundreds to thousands of these per kidney. And most of these are found in the renal medulla. They're found in the renal pelvis. In the renal pyramids. Remember, the renal pyramids is this folding pattern in order to increase surface area. So we can have lots and lots and lots of these nephrons in each renal pyramid. And that's going to allow, that's like having hundreds and hundreds and hundreds of vacuums cleaning a building. Now, In the glomerulus, this is where I won't say gas exchange. This is where the waste product exchange is going to take place. Well, the problem with the nephron is what we call non-specific. Now, what I mean by that, okay. In the case of the nephron, just like your vacuum, it is non-specific. The nephron here at what we call the glomerulus capsule or the Bowman's capsule, we're going to do what's called filtration. And you're going to see a formal definition of filtration here in a minute. But this is where the blood gets filtered. Well, it's pretty much just due by, you can think of it as suction. The nephron is made from smooth muscle, so it will peristalse. That will help create a suction. At the same time, we're dealing with osmosis and diffusion, things going from an area of high pressure to an area of low, or high concentration to an area of low concentration. Well, just like your vacuum is non-specific. It's just creating a suction to suck things up off the floor. Your vacuum doesn't know, is something a piece of dust or is something a diamond? It's just creating a suction and sucking things up off the floor. The same thing happens in our nephron. Here at the glomerulus, we're going to do filtration, and filtration is non-specific. Just due to what we call negative pressure, the nephron is peristalsing. That's going to help create a suction. At the same time, we have diffusion and osmosis taking place. Things are going to get sucked into the nephron. And the nephron doesn't know if this is a good thing or if this is a bad thing. So at the glomerulus, I say at this point in time, we have empty blood. The afferent arteriole has dirty blood, and then the glomerulus, all the dirt gets, think of it as getting sucked up off the floor. But at the same time, nutrients are also going to get sucked out because we're just dealing with laws of diffusion. And the nephron doesn't know what's a nutrient and what's a waste product. So at this point in time, when the blood is filtered, the capillaries are going to come back together to form what's called an efferent arteriole. And that is what you're seeing right here. Okay? That is an efferent arteriole. This is one of the only places in our body that a capillary does not come back together to form a venule. Because think of it this way, efferent arterioles carry empty blood. This is blood that has been filtered, but we have not only filtered out the bad stuff, we also filtered out the good stuff. So we are going to have to do something called reabsorption. We need to get the good stuff back into our bloodstream. So at the efferent arteriole, your glomerulus comes together to form your efferent arteriole. And then your efferent arteriole will again split to form all of these blood vessels here. Okay? These are all what we call peritubular capillaries. Peri meaning around, and tubular meaning the tube. So these capillaries are surrounding this nephron, is surrounding this tube. And this is where reabsorption will take place. It's also where something called secretion is going to take place. But we need to make sure that we get as much nutrients back into our bloodstream as possible. And then the peritubular capillaries will eventually come back together to form venules. And that's what this little guy is right here. That would be a little venule. And then your venules will come back together to form this guy here, an interlobular vein. And then your interlobular veins will all come together to form your renal vein. So you can think of the artery as carrying dirty blood, the renal artery carrying dirty blood into the kidneys, and the renal veins are going to be carrying clean blood out of the kidneys. So in the case of the nephron does have these three parts. Okay? We have this thing called the glomerulus, okay, which is your capillary. It's actually not part of the nephron, but it's, supplying blood to the nephron. You then have this thing called the Bowman's capsule. It's also called the glomerulus capsule. This is this little cup shape that surrounds the glomerulus. And I always draw it without all these twists and tubes. So we would have the Bowman's capsule, and then the Bowman's capsule is going to lead to this series, as you can see here, of convolutions. Remember, convolution is a fold. And this region here is what we call the proximal convoluted tubule. Proximal because it's close to the glomerulus, convoluted because it's folded. And remember, folds increase surface area. This is where most of our reabsorption is going to take place. And I'm going to talk about how this happens in a minute. We need these folds, we need the surface area to make sure we get a chance to reabsorb our nutrients. So this right here would be our Bowman's capsule. This would be the proximal convoluted tubule, what we call the PCT. It then dips down into what we call the loop of Henle. Now we would have a descending loop of Henle, we would have an ascending loop of Henle, and you can see here in this picture that the loop of Henle actually gets smaller. The loop of Henle relies on pressure changes in order to force things out of the nephron. Pretty much as long as you're on this side of the loop of Henle, you have a chance of being reabsorbed. You have a chance of getting added back to the bloodstream. However, when you're on this side of the loop of Henle, what we call the ascending loop of Henle, oops, sorry, I got this backed up. Okay, oops. Right. If this is your DCT up here, this is your descending loop of Henle, and then it's going to come back around to form your ascending loop of Henle. By the time you're in the ascending loop of Henle, you're considered a waste product. You're going to be part of urine. You're going to get dispersed. From your loop of Henle, you go into another convoluted tubule, which we call the DCT, the distal convoluted tubule. And usually by the time the fluid or the solute reaches the DCT, it's a waste product. This is going to be urine. Everything that's in there should just be waste products. Any nutrients that are left in there are probably going to be lost. And then the DCT dumps into this thing here called the collecting duct. Now the collecting duct is shared. Okay, several different nephrons will dump their urine into one collecting duct. That's why it's called the collecting duct. It's going to collect urine from all these different tubes. So you can see that there would be another tube joined here, there would be another tube joined here, there would be another tube joined here. And we don't have a lot of blood vessels around the collecting duct because in the collecting duct you are urine. And we don't want to accidentally reabsorb harmful waste products. So like I was mentioning, how the kidneys make urine is actually fairly simple. It is due mostly to peristalsis and to filtration. In the case of filtration, if you remember, the process of filtering, it's going to be non-specific. It's going to filter all the substances out because it's due almost entirely to diffusion. Now your nephron, again, is made from smooth muscle, and smooth muscle does peristalse. And so from the peristalsing, it's going to kind of create a suction, just like sucking things up a tube, like a straw. So that's going to help also pull, nutrients that are diffusing out of the glomerulus into this vacuum, into this tube. So it is due entirely to diffusion. So filtration is non-specific. It can't say what to filter. It's just going to filter everything out. And this is going to happen between the glomerulus and the Bowman's capsule. Then we're going to go into reabsorption. And reabsorption is controlled entirely by hormones. And I'm going to talk about that here in just a second. But reabsorption tends to happen in the PCT, the proximal convoluted tubule, and the descending loop of Henle. And reabsorption, this is how our body is going to put the nutrients that just got vacuumed up back into our bloodstream. Because we don't want nutrients being lost in our urine. Okay? We need to make sure that any nutrients that get lost goes back into our bloodstream. And then we have secretion. Secretion happens in the ascending loop of Henle and the distal convoluted tubule. This is kind of like a last-ditch effort to make sure that the bad stuff is in the urine. And all of this is controlled by a hormone called ADH or vasopressin. ADH stands for anti-diuretic hormone. It's also called vasopressin. Vasopressin is kind of the old name. Science is renaming a lot of stuff to give you a clue as to what it does, as you're going to see here. So in the case of hormonal control of the kidneys, the making of urine is a negative feedback mechanism, meaning you're going to have two hormones to control how much urine we get made. And the first one here is a hormone called ADH, or anti-diuretic hormone. It's also called vasopressin. This hormone controls how much water kidneys put into the urine. Think of it this way. Here we have our glomerulus, and here we have our proximal convoluted tubule, our loop of Henle, our distal convoluted tubule, and our collecting duct. Think of the proximal convoluted tubule. Now, it's not really like this, but this analogy is the easiest way for people to understand what's happening here. Think of the proximal convoluted tubule as having doors along it. And those doors are shut. Now remember, down here, it's hard to draw red on red, so I'm going to draw green. Down here, we have capillaries. Well, what ADH is going to do is control how many of these doors are allowed to open. Think of it, again, in reality, it's not quite like this, but this is the easiest analogy to show how things can be reabsorbed. So let's just think of the PCT, the proximal convoluted tubules, as having doors. And these doors are shut. ADH's job is to act as a key. It will tell these doors to open. It basically allows the kidneys to know, okay, how much stuff am I going to release? So what happens is, remember, we've got a whole bunch of nutrients piled up inside of our PCT. So let's say I've got some potassium, I've got some calcium, I might have some sodium. I have all this stuff inside my DCT, and these are nutrients that my body needs. I need to get them out of the urine and put them back into my bloodstream. So ADH will basically tell these doors, these hypothetical doors, to open. And when these hypothetical doors open, these nutrients can leave and get reabsorbed by the bloodstream. Well, these are all ions. These are salts. So if I have a lot of doors open, I have a lot of ions entering my bloodstream. So therefore, my blood is getting thicker and more dense. So now water will leave my nephron and water will re-enter my bloodstream. Osmosis, in order to counteract so my blood does not get too thick. So the more ADH, or the more vasopressin that the hypothalamus makes, the more of these doors are going to get opened. So the more stuff you reabsorb, so the more water gets put back into our bloodstream. Therefore, you will have less urine. Kind of confusing. The more hormone, the more doors, the more reabsorption, the less urine you're going to make. Because we just allowed water to leave the nephron and go back into the kidney. So we just allowed water to be reabsorbed into our bloodstream. So if water gets reabsorbed into our bloodstream, that's less water running through these tubes. And therefore, you're going to have less urine. Now, this hormone, again, we said was a negative feedback. So its opposite is a hormone called aldosterone. It's made by your adrenal gland, and it works with a negative feedback. It promotes salt retention. Now, what that means is that this hormone tells you to close the doors. So if you close the doors, salt stays in the vacuum tube called the nephron. So water will stay in the vacuum tube called the nephron. So you're going to make more urine. And pause this, rewind it, if you need a little bit more help understanding what's going on. So like I said here in this picture, you can see this blue. That would be the, like the example of the renal, or let's start with this red here. This right here would be your arteriole. And this would be an even smaller arteriole leading to the glomerulus. These are your peritubular capillaries. And this would be like a venule coming back into another venule, which will eventually lead to your renal vein. Okay. Right here, we have the glomerulus. Here we have the PCT. You can see here the loop of Henle. This would be the DCT. And here you have your collecting duct. All right. Now, last but not least, some problems that we can have. And remember, most of these are genetic and they're hormonal. The first one here, if you make too much ADH. if you make too much ADH, you're going to have a lot of those hypothetical doors open. So you're going to have a lot of diffusion back into the bloodstream. You're going to have a lot of osmosis back into the bloodstream. So you don't make a lot of urine because urine has water in it. So you will reabsorb large amounts of water, making your urine very, very, very concentrated, if you're able to make urine at all. Okay. Now, if you make way too much ADH, you can do what's called anuria. Anuria is where you don't make urine at all, and that is not a good thing. Okay, that's usually a sign of either a tumor with the hypothalamus or a tumor with part of your pituitary gland or some type of genetic problem or severe dehydration. You can also have oliguria, which is where you make small amounts of urine. And this is, sometimes, if you, like I tend to be naturally dehydrated. I don't drink a lot during the day. So I don't, go to the restroom that often during the day. But this, that's not oliguria. These are people that, maybe make urine and they usually use the restroom maybe once or twice every 2 or 3 days. This can lead to a condition called suppression. Suppression is when the kidneys just stop working. Okay? It's also called renal failure. Right? Suppression can lead, this can lead to a condition called suppression, and this is where the kidneys will not make urine at all. So this is what's also called renal failure, and these people have to go on the dialysis machines in order to take these nitrogenous waste out of their bloodstream. Now that's different than retention. In retention, your kidneys are working fine. In retention, you're making urine. And in retention, your bladder is filling up. However, you can't pee. Retention tends to be a problem in males, and this tends to be a sign of prostate cancer. Remember, the trigon is a sphincter muscle at the base of our bladder that leads to our urethra. And this sphincter muscle opens and closes in order to allow us to urinate. Well, if you remember, the prostate gland is a circular gland, and the urethra passes through the prostate gland. So if the prostate gland has a tumor in it, it can squeeze the urethra, or it can actually push up on part of the bladder. So it'd be like you taking a garden hose and bending it in half. And if you have prostate cancer, that tumor can actually squeeze on your urethra to the point that urine cannot come out. So your kidneys are working fine, your bladder's filling up with urine, but you can't go to the bathroom. And so a lot of times you would have to be catheterized. Now, as we get older, our muscles get tired. And so as we get older, we're all going to run across something called incontinence. Ladies, if you become pregnant, this will probably happen. This is what things like depends are for. As you get older, your muscles get tired. And your trigon, that sphincter muscle, is not going to work as well. So it's not going to be able to squeeze tight as well. So you might dribble a little bit. And ladies, when you're pregnant and all that extra weight is pressing on your bladder, okay, you're going to dribble a little bit. That's what incontinence is. Then we have bedwetting. Bedwetting has a real name. It's called anersis. And remember, your trigon is one of the only sphincter muscles in your body that is voluntary. You had to learn to be potty trained. Well, children, you teach them to be potty trained. You teach them to, okay, they feel they need to go to the bathroom. So they learn how to hold it, and they learn the feeling of going to the bathroom, but that's when they're conscious. When you're asleep, it's a whole different story. The young brain has to figure out, okay, I'm asleep, what am I doing? And so it takes a little while for that young person's brain to figure out, okay, let me wake this young person up and tell this young person to go to the bathroom. Okay. It takes a little while for your brain to figure out what's going on. And so it's very natural for young people, and when I say young people, I'm talking about little kids, to wet the bed. But some children will wet the bed longer. It takes their brain a little bit longer to get used to this. And some children, I was very lucky. My daughter, we probably only had 2 instances of bedwetting once she was potty trained. So it just really depends on that person's brain.